Hi there, and welcome to this lecture on process flow diagrams, importance of PFDs. My name is Marina Milicic. Let's discuss why process flow diagrams are vital to chemical engineering design. Because there's so much usable information, process flow diagrams are considered the most important comprehensive diagram in chemical engineering. In process design, you will most likely spend the bulk of your time building and optimizing a process flow diagram. This diagram is so important because it represents the main information necessary to understand what it will take to build the process. If we know what product we want to make, how much we should make, and a general understanding of the equipment requirements, we can see very quickly if we're able to make a profit with the process. In engineering, you don't need to perform an extremely detailed economic analysis where the cost of every pound of steam and every valve is calculated to fine precision. You really only need to have a general idea of your profit potential in order to see if it's beneficial to move forward with the project. This is where a process flow diagram is key. It provides just enough information to determine if the project should go to the next stage of detailed design. As an engineer, you don't have years to calculate the profit potential of a project. Management probably wants it done as soon as possible, and you most likely only have a few months, if that. You must communicate with some level of confidence and objectivity the profitability of the project. And if a process is not profitable, this is also very valuable information because it would be a waste of time, money, and resources to build the plant. Lastly, we can also use process flow diagrams to quickly compare different processes making the same product or different processes making different products. Through this side-by-side comparison, we can determine which processes are most profitable and also more easily see their advantages and disadvantages. This sample process flow diagram I created is probably one of the simplest you'll ever see. Most diagrams of this type are far more complicated than this, oftentimes with at least 20 pieces of equipment. This is why process flow diagrams are usually printed on 24-inch by 36-inch paper and are not meant to be shrunk down to a small page like this. But this sample process will be useful in helping us better visualize and understand these diagrams. Notice first and foremost that this process flow diagram has a figure number and caption, which is important so that the reader knows the purpose of the diagram and what product is being made. Without a figure number, you can't refer to the diagram in a report, making this a simple yet critical addition to this diagram. Notice also that the most relevant reactions are included in the diagram. The main desired reaction should be listed first, and any other important side or parallel reactions are also listed. The reactions are also labeled as desired or undesired. If including all the reactions on the diagram creates too much clutter, try to limit the number to 1 to 5 reactions. Notice also, since chemical formulas may represent a number of isomers, you should consider putting the name of the chemical under non-obvious formulas. People who do not have a chemistry or chemical engineering background may be reading this diagram and will need to quickly and accurately identify the names of the chemicals involved in the process. At this point, I'll briefly guide you through this process from start to finish. This process takes oxygen and ethylene in separate streams and compresses and heats them before combining them and sending them to a packed bed reactor. Through a catalyzed reaction, ethylene oxide and undesired carbon dioxide and water are created. The main reaction does not feature 100% conversion of the reactants, so this means that ethylene oxide, along with unreacted ethylene, oxygen, water, and carbon dioxide, come out of the reactor and are cooled down by a heat exchanger before going into the first of 2 flash separators. Here the oxygen and carbon dioxide are separated, depressurized through a turbine, and vented into the atmosphere. This flash was not able to separate all of the lighter gases, so the bottom stream is sent to another flash unit, where the rest of the oxygen and carbon dioxide are depressurized through a valve before being vented. The ethylene, ethylene oxide, and water are sent to a freon-cooled heat exchanger, and then to the first of two distillation columns, where the ethylene comes out from the distillate because it's more volatile than the ethylene oxide and water, which are sent to the bottoms. Ethylene is recycled back to the reactor to help increase the overall conversion. Before being further separated, the liquid ethylene oxide and water stream are sent to a pump to help increase the pressure, which helps facilitate their separation. In the second distillation column, ethylene oxide is separated in the distillate, while water is removed from the bottoms. Let's next look at some basic characteristics of this diagram. All pieces of equipment involved in reacting, separating, pressurizing, depressurizing, heating, and cooling are represented. The equipment shown include reactors, all separators, including single-stage separators or flashes, compressors for pressurizing gases, pumps for pressurizing liquids, turbines for depressurizing gases and vapors, valves for depressurizing gases or liquids, heat exchangers for heating and for cooling. And though there isn't one in this process, fired heaters or furnaces are also shown, and storage tanks are sometimes shown on a process flow diagram, but not always. One last point, just as with block flow diagrams, when lines need to cross on a diagram such as this, the horizontal line stays solid and the vertical is broken.